Let us look at an example of transportation model with multiple optimal solutions. So sometimes there may be cases with a transportation problem which might end up having multiple optimal solutions, and each of those optimal solutions may have the same transportation cost. Now, it is definitely beneficial for the organization to know these alternate optimal solutions because these provide flexibility in the decision making process. So, a two factory, three warehouse balanced transportation problem of a company is given below. So, there is a company which has two factories, F1 and F2, and three warehouses, P, Q, and R. So let's say the first plant is here, F1, and the second plant is somewhere here, which we denote as F2. Now F1 has a supply capacity of 250 units. So supply capacity is 250 units, while F2 has a supply capacity of 100 units. So for F2 supply capacity is 100 units. Now there are three warehouses, P, Q, and R. So let's say this is P, this is Q, and this is R. Now P has a demand of 150 units. So D is 150 units. Q has a demand of 80 units. So D is 80 units. And R has a demand of 120 units. So demand is 120 units. Now each of the factories can transport the material to each of the warehouses. So F1 can ship material to P, and from F1 to P the unit cost of shipping is 12 rupees. That is, for each unit which is shipped from F1 to P, the cost is 12 rupees. So 12 rupees per unit. We can also transport from F1 to Q, and the cost is 18 rupees per unit. And similarly F1 to R, and the cost is 14 rupees per unit. Similarly from F2 to P, the transportation cost is 13 rupees per unit. From F2 to Q, the transportation cost is 17 rupees per unit. And F2 to R, transportation cost is 13 rupees per unit. So with this information given to us, we have to find out how much should be transported from each of these two factories to these warehouses such that the demand and supply constraints are not violated, and at the same time the overall transportation cost is the minimum. And we have also been asked to identify if there are multiple optimal solutions for this problem, and if so, what are those? So let's see how we can use the transportation model to obtain a solution to this problem. Now the first step in solving the transportation problem is to formulate a transportation table. In this step, we have to express the supply from origin, requirements at destination, and the cost of shipping from origins to the destination in the form of a matrix. Now in this example, we have already been given the transportation table. So let me note down the transportation table here. So this is the transportation table that has been given to us in this example. On the left hand side we have the plants F1 and F2, and on the right hand side we have the capacity for each of these plants. On the top we have the warehouses P, Q and R, and at the bottom we have the individual demand for these warehouses. In the middle we have the unit cost of shipping. Now once we have formulated the transportation table, a check needs to be done to find out if the total supply and demand are equal to each other. So let's quickly calculate it. So we have supply equal to 350 and the demand is 80 plus 120 is 200 plus 150 is 350. So demand and supply both are equal to 350. So this is a balanced transportation problem. Now the next step is to find out the basic initial feasible solution. So let's use the Vogel's approximation method to find out the initial feasible solution. Now in Vogel's approximation method, the first step is to calculate the difference between the two minimum elements for each row and each column. So let's start row wise. So for the first row, the minimum cost is 12 and the next minimum cost is 14. So 14 minus 12 is 2. For the next row, the minimum is 13 and the next minimum is also 13. So this will be 0. Now for the columns, for the first column it is 13 minus 12, which is 1. For the second column it is 18 minus 17, which is again 1. And for the third column it is 14 minus 13, which is again 1. Now the next step is to select the row or column with the largest difference. So F1, that is the first row, has the largest difference of 2. The next step is to allocate the maximum number of units to the square with the minimum cost for the selected row. So the square with the minimum cost is F1P. So let's try to allocate the maximum we can to this square. So F1 has a supply capacity of 250 units, while P has a demand of 150 units. So even though F1 can supply more, the demand at P is only 150 units. So the maximum we can allocate is 150. Now with this allocation, the entire demand for P has been met, so the remaining demand is 0, while the remaining supply capacity at F1 is now 250 minus 150, which is 100. Now since the entire demand for P has been met, let's cross off the remaining squares for this warehouse, indicating that it is no longer required to be allocated. Now let's again redetermine the row and column differences. So for the first row, the lowest is 14 and the next lowest is 18. So difference is 18 minus 14, which is 4. For the second row, 17 minus 13, which is again 4. Now for the columns, the first column we can skip as it is completely allocated. For the second column, the difference is 18 minus 17, which is 1. And for the third column, it is 14 minus 13, which is also 1. So now we have to select the row or column with the largest difference. Now we have a tie here between F1 and F2. So ideally we can select any one of these, but if we select the one where we get the maximum cost benefit, then we'll have to go through fewer iterations to arrive at the optimal solution. Now when I say the maximum benefit, means the unit cost for allocation should be lower than the other option and the number of units may be more. So let's first compare the unit cost. So for the first row, the lowest unit cost is 14, while for the second row, the lowest unit cost is 13. So we should select the second row because we get the lower unit cost if we select this row. So now let's try to allocate the maximum we can to F2R because it has the lowest cost for F2. So F2 has a supply capacity of 100 while R has a demand of 120. So the maximum that can be allocated is 100. So with this allocation, the remaining demand at R is 20 while the supply remaining at F2 is 0. So now since the entire supply capacity at F2 has been exhausted, let's cross off the remaining squares for this row, indicating that they are no longer available for allocation. So now we are left with one row and two squares. Let's try to allocate to the one with the lower unit cost, which is F1R. So for F1R, the supply capacity available is 100 while the demand is 20. So the maximum we can allocate is 20 units here. So with this allocation, the supply capacity at F1 becomes 80 while the demand at R becomes 0. Now the last square available is F1Q. The supply available is 80 and the demand is 80 as well. So we can allocate 80 units here. So with this allocation, the supply capacity at F1 becomes 0 and the demand at Q also becomes 0. So this becomes our basic initial feasible solution. Now let's find out the total cost of transportation. So the total cost of transportation will be equal to the multiplication of the unit cost of shipping with the number of units being shipped at each route. So for example, the first one, it is 12 multiplied by 150 plus 18 multiplied by 80 plus 14 multiplied by 20 plus 13 multiplied by 100. So let me pull my calculator here. So 12 multiplied by 150 plus 18 multiplied by 80 plus 14 multiplied by 20 plus 13 multiplied by 100, 4820. So 4820 rupees is the total cost of transportation that we have achieved after the basic initial feasible solution. So at this point, we have a solution in hand using which we can transport the material from the factories to the warehouses without violating the supply and demand constraints given to us. However, we are not sure if this is the lowest transportation cost that can be achieved. So what we need to do to determine whether this is the optimal solution or not. So we need to perform an optimality test. Now before we can perform an optimality test, we have to find out if this solution is acceptable to perform an optimality test. Now the first condition for optimality test is that the number of allocations should be equal to m plus n minus 1, where m is the number of rows and n is the number of columns. So we have 2 rows and 3 columns. So this becomes 2 plus 3, 5 minus 1, which is 4. Now let's find out the number of allocations that we have. So we have 1, 2, 3 and 4 allocations. So the first condition here has been met. Now the second condition is that these allocations should be in independent positions. Now we can check if the allocations are in independent positions by using a simple rule of thumb, which is that it is impossible to travel from any allocation back to itself by a series of horizontal and vertical jumps from one occupied cell to another without a direct reversal of the route. So let's try one of the cells, which is F1R. Now from here we have to form a closed loop and come back to this cell using horizontal and vertical jumps from the occupied cells. So from here we can go to F1Q or we can go to F1P, but from there we can't have any horizontal or vertical jump using which we can come back to F1R. So what this means is that this allocation F1R is an independent position, and if you note, you'll find that all the other allocations are also in independent positions, so which means that the second condition is also met. So now we can proceed with the optimality test. So let me clear off this closed path which I was trying to create. So now let's proceed with the optimality test. For this example, we'll use the stepping stone method. Now the first step in the stepping stone method is to proceed row by row and select a water square. Now water square are the squares which do not have any allocations. So the first row does not have any water square. The second row has water squares F2P and F2Q. Now the next step is to establish a closed path using rectilinear motions. That is moving horizontally and vertically only, starting from the selected water square via stone squares and then back to the same water square. Now a right angle turn is made only at the stone square, even though the path may skip over stone and water squares. So the first water square is F2P. So let's try to create a closed path for this water square. Now from here we can go to F1P, then to F1R, then to F2R, and then back to F2P. And the second water square is F2Q. So let's create a closed path for this square as well. So from F2Q we can move to F1Q, then F1R, then F2R, and then back to F2Q. So basically what we are doing here is we are trying to find out that if we move any of these allocations to the water squares where there is no allocation currently, then will it be beneficial for the total cost? That is, will the total cost of transportation reduce? So we have formulated the closed path saying that if we allocate anything to the water squares here on this path, then there has to be a corresponding change in the other allocations so as to comply with the demand and supply constraints given to us. So for the same thought, the next step is to assign the alternate plus and minus signs on the closed path, starting with a plus sign on the water square. So the first water square is F2P. So we are saying that we are going to add allocations to this square. So there's a plus sign. Now if we add here, we have to subtract from F1P. Then we have to add to F1R and subtract from F2R. Similarly, a plus sign at F2Q, negative at F1Q, positive at F1R, and negative at F2R. The next step is to calculate the net cost change for the path. The net cost change is obtained by summing up the unit cost of each cell on the path. So for F2P, the closed path was F2P minus F1P plus F1R minus F2R. The unit costs are 13 minus 12 plus 14 minus 13. So 13 gets cancelled with 13, 14 minus 12 is 2, so this is 2. For the next water square, which is F2Q, so the unit cost value is 17 minus 18 plus 14 minus 13. 17 minus 18 is minus 1 plus 14 is 13, and 13 minus 13 is 0. Now the next step is to evaluate the solution for optimality by observing the sign of the net cost change. So if there is any net cost change value which has a negative value, then it means that there is a potential for improving the total cost by making allocations to that square. But here we don't have any negative values, which means that the solution that we had is an optimal solution. However, we have a value of 0 for one of the squares. Now this net cost change value of 0 indicates that if allocations are made to this square, then the solution will continue to have the same total cost which was obtained earlier, which means that there is an alternate optimal solution. So let's now obtain the alternate optimal solution by moving the allocations to this water square, which is F2Q. So we'll take the closed path F2Q, F1Q, F1R and F2R. And on this closed path, what we'll try to do is add allocations to this square F2Q. So in order to do that, we have to subtract the maximum possible units from each negative sign square and add into each positive sign square on the closed path. So the maximum we can subtract from the negative sign squares is 80, because if we subtract more, then this value become negative, and that is not possible. So we have to subtract 80 and we have to add 80 to the other squares. So the allocation here becomes 80. In F1Q it becomes 0. For F1R it becomes 20 plus 80, which is 100. And for F2R it becomes 100 minus 80, which is 20. So let's note down this solution. Now let's add the unit cost values. So the first solution that we had obtained had these allocations. Now let's note down the second solution that we obtained. So this is the first solution and this is the second solution. Now let's again validate the cost obtained by using both of these solutions. So for the first one, 150 multiplied by 12 plus 80 multiplied by 18 plus 20 multiplied by 14 plus 100 multiplied by 13, which is 4820. So that was what we had obtained earlier. Now let's compare with the second solution. So 150 multiplied by 12 plus 100 multiplied by 14 plus 80 multiplied by 17 plus 20 multiplied by 13. So this is also 4820. So both the solutions have the same total cost of transportation, but basically these are two different routes that give flexibility in the decision making process. And both of them represent an optimal solution because there was no negative net cost change value in the optimality test.